All right. So we're at a point in the semester where everyone has kind of gotten spread out quite a bit. We have some students who are a little bit ahead and some students who are a ways back. So I'm trying to, with these videos, still post stuff that's relevant to as much of the class as possible. And it looked like 6.3 might be a good place to help out with something. So this is homework 6.3.1. And what you see over here is a plate, a big plate that is suspended by three cables, A, B, and C. And what we're given is this diagram, and they tell us that the plate is uniform. So it also has this force, and we're given these lengths, and led to believe this is rectangular. So we can assume that L1 and L, whatever this is over here, are the same size or the same length. Uh, so they give us a few different things, and then they also want us to find, what we're asked to find is the tension in A and B and C. So this is a fairly straightforward problem, at least it feels fairly straightforward when we start. And what we are basically going to do is try to sum forces in the x direction and then do whatever else we have to do to get enough information to solve for the tension in those cables. So let's do our free body diagram first down here. Uh, I really like how they set this up for us and kind of help us to see it. There's one, um, this should be pretty straightforward, that there's going to be tension in A. It's going to be pulling up on that. It's going to be pulling up at B. It's going to be pulling up at C. Obviously F is going down, and then G, which they kind of give us a hint there that uh, the weight of the plate, even though we know in our minds that the weight is pulling down all over the plate, it's kind of a uniform distribution. We're going to simplify it and imagine that the force is all concentrated at the center of the plate and that it's pulling down just from there. So we'll put our force down there and then say, how did I do? Show me what it actually looks like, and guess what? We got it right. So we've got A, B, and C pulling up, G pulling down, and F pulling down. Now, the reason that it's important to know that the reason it's important that we know that we're putting this at the center, or the centroid is what it's called, is because that's going to help us later on when we have to deal with moments in this problem. We will have to deal with some moments. So let's, over here in Mathematica, I've kind of already got it set up. So we put in our force, our weight of the plate, distance L1, L2, and L3. So I'll just hit Shift Enter to get those processed by Mathematica. And I'll let you guys read through this later if you want to. One thing that I should mention, this problem, because this will be useful in later problems, perhaps. The problem here gave us the weight of the plate all is in one number. It just said the whole plate weighs 1,000 newtons. It could have done it a different way. It could have said the plate weighs 25 newtons per square meter or something like that. Or it could have said the density of the steel that this plate is made of is, 70 kilograms per cubic centimeter or something like that, and then given us the thickness of the plate. My point in telling you that is that I want you to think about how would you, if this was not a regular shape like a rectangle, how would you find an equivalent force coming down due to the weight of an irregular shape? Say this was shaped like, I don't know, imagine something other than a rectangle, but that could be broken down into rectangles. Uh, and the obvious answer is, well, even with this one, what you could do is you could draw a grid on it and have, like, say, each square meter, and have a weight or a force due to weight arrow coming down from the center of that square. So if I were to take and break this up into a grid shape, then I'd have, a 9 or 12 or however many grid shapes I decide to break it down into, and have the force equivalent for each one of those coming down. So you don't have to just have a rectangle to be able to do this, what we're going to do. So I'll move on. But let's do what we normally do, and let's try summing the forces. We know, obviously, that there aren't going to be any forces in the x or the y direction, so that makes things a little bit easier on us. Let's start by summing forces in the z direction. So to get that fun sigma symbol, I'll show you how to do that. You do escape, and then capital S, and then escape again, and now I have sum of the forces in Z. So I'm going to have tension in A, tension in B, and tension in C, and those are all positive because they're going up, like we remember from our free body diagram. And then I'm going to have F as a negative force and the weight of the plate as a negative force. And then shift enter. And what I recognize here when I do that is, okay, I know the force and I know the weight of the plate, and that's it. I don't know anything else yet. I have three unknowns. I have these three unknown variables, and those just happen to be what I'm trying to solve for. So let's keep working on that. Let's try, what can we do next to get us some more information? I need more equations if I'm going to have enough equations to match the number of unknowns that I have. Well, we could take a moment. We could take a moment technically about any point on here. I chose A, so I'll do the moment at point A about the x-axis. So what I need to do now is make sure that I'm thinking correctly about what's positive and what's negative. If I'm looking down the positive x-axis towards the origin, towards the z-axis or the y-axis, so if I'm standing on that left-hand side, looking down the x-axis, and I hold my hand up, my right hand in front of my face, and have my thumb along the x-axis, curling my fingers into a fist, that is a positive moment if it's counterclockwise, if that's the way that the force moves it. If the force causes the plate to want to rotate backwards clockwise so that my wrist bends back, if I'm holding my thumb along the x-axis, then that's a negative moment. So in this case, looking down the x-axis towards the z-axis, towards the origin, then the tension in B pulling up towards point B times L1, because that's the arm, that's the distance from the x-axis to the line that force B is acting on. So this distance right here is my moment arm, and this is where the force is applied. That is a positive moment because it's pulling clockwise, or counterclockwise, sorry, it's pulling counterclockwise around axis X. So that's a positive moment. And then if I have C, that's also going to be positive, and you can probably see why. I've got the x-axis, L1 is my moment arm, and C, the tension in C is pulling up, so that again is making a counterclockwise moment around axis X. So that's another positive moment. Now, from here it's fairly easy because, well, force F is pointing the opposite direction. It's the same distance away from X, so it's negative F times L1. And then the weight of the plate, like we saw down here, is similar, but its distance is a little bit different. It's halfway between the x-axis and this outer edge. So it's L1 divided by 2. So that is the sum of the moments at point A about axis X. Now I can do the same thing for the sum of the moments at point C, which was the next one I chose. You could have chosen a different point if you wanted to, but I chose to do it about point C, or at point C about axis Y. So now I'm looking this way from point Y, from out here somewhere in front of this, looking down the y-axis towards Z. So now things are going to be a little bit different because I'm rotating this way around axis Y. So in this case, the force due to F here, the applied force, is going to have a moment arm of L3. And now if I'm standing at here outside, kind of where this Y is, looking down the y-axis towards Z, and I hold my right hand up in front of my face, stick my thumb out, have it along the y-axis, and rotate my fingers into a fist, that's a positive moment. So F is going to cause a positive moment because it's curling my fingers down, right? So that's going to be a positive moment times L3, that's the moment arm. And then tension in B is going to move the opposite direction. It's going to curl my wrist back, and it's going to be distance L2 plus L3. Tension in A, same story. L2 and L3 are the moment arm. And then the weight of the plate is going to be a positive moment, and it's going to be L2 plus L3. It gives me that whole length of that side divided by 2. If L2 and L3 were equal, then I could just use either one of them, but they're not. So we've got to take them and divide it by 2. So now I've got 3 equations, some of the forces in Z, some of the moments at point A about X, some of the moments at point C about Y, and I have 3 unknowns. I didn't introduce any new different unknowns, just TA, TB, and TC. So what I'll do then is I'll have Mathematica do the hard work and the hard algebra and solve all 3 equations for me simultaneously and tell me what TA, TB, and TC are. So you type it in this way, you say solve, you do a square bracket, and then close the square bracket and put / capital N. And then in the middle, you're going to have first a set of curly brackets that you're going to put your equations in, and then a comma, and then tell Mathematica what you're looking for, TA, TB, and TC, and make sure you get these exactly right. They've got to be capitalized the same way as TA, TB, and TC in your equations. And make sure that you hit the double equal sign too when you put in your equation. So we've got some of the forces in Z set equal to 0, some of the moments at A about X equals 0, and same for that one. And then we'll hit Shift Enter to solve it. And what does it give us? Oh, I forgot to update these. Alright, now it recognizes it, and voila, we get the tension in A is 500, tension in B is 214, and tension in C is 786. We'll round. So there you go. Let me know if you have any questions.